Hello and welcome back to Mr. Latham's AQA revision sessions. So this is part 2 of motion, and the point of this video is simply to go through with you some example questions that they could ask you on your exam. So to start off with, we have our first question, which is showing a student's motion on a playground. And before I even look at the questions, the first thing I'm going to do is, when I look at this graph, I'm going to have a look down the side and see that over here we have distance. So this is a distance time graph, and that is something I'm going to be keeping in mind when I'm answering these questions. So to start off with, question number 1, describe the motion of the student over the 18-second period. So first thing I'm going to look at here is that's 18 seconds, so I need to make sure that I'm describing the correct parts of the graph. So it said for the first 18 seconds, so it is from 0, and we have 15, 16, 17, 18. So in this case, it is actually asking me to describe the entire journey. Now they might not, in an exam they could ask you to just describe part of it, so it is important to make sure that you are describing just the element that they want you to talk about. So let's have a look. What have we got? Well, we can see it's a distance time graph. We can see that as time goes by, to start off with, that as time goes by, the distance is increasing. So I could say over here, I'm just going to put a cross there. So for the first 5 seconds, so from 0 to 5 seconds, so from 0 to 5 seconds, we can say that the object is increasing its distance. Okay, so therefore it is travelling at a constant speed. So from 0 to 5 seconds, the object is moving at a constant speed. Okay, so next then, so what about for the next few seconds? So let's put a cross there just so I can separate it. So we could say from 5, 6, 7, 8 seconds now. So from 5 to 8 seconds, the object has, well, its distance isn't changing as time goes by, therefore the object must have stopped. So the object is stationary. And then our next bit, our last part, we can see from 8 seconds all the way down to 18 seconds. So for the last part of the graph, we can see that the distance is decreasing with time, and therefore if the distance is decreasing, the object must be moving in the opposite direction. So from 8 seconds to 18 seconds, the object is moving at a constant speed, and I know it's a constant speed because it is a straight line, and it is moving at a constant speed in the opposite direction. And there we have it. So there is a description of the motion of the object, in this case a student. Okay, so number 2, calculate the distance travelled by the student. So how would we calculate the distance travelled on a distance time graph? Well, let's have a look. So we start off at 0. The person moves, the student moves up to 10 meters at this point here, and then they stay at 10 meters, and then we see that they then move in the opposite direction all the way back down to 0. So that's a relatively straightforward question. So they move 10 meters away, and then they move 10 meters to get back to the starting point. Therefore, the student is moving, or the student moves 20 meters on this graph. Okay, that's a relatively straightforward one. So our third one, calculate the speed of the student at 3 seconds and at 15 seconds. So this is a 2-part question. So what do we need to do for this one? So calculate the speed of the student at 3 seconds. So let's find 3 seconds first. So we have 1 second, 2 seconds, 3 seconds. So it's at this point here. Okay, so I can see at this point there is a line that's moving upwards, and so what is it asking us? Well, it's asking us for the speed, and we know that speed is distance divided by time. Therefore, as with the example on the last video, they are asking us for the gradient of the line. So how do we calculate the gradient of the line? Well, it is rise over run. So what is our rise and what is our run? So start off with, I'm going to separate this up into a triangle. And it doesn't really matter where you make the triangle. The rule of thumb is generally make it as large as possible. So I've just made it as large as I can. So the whole triangle here. And then let's calculate our rise and our run. So start off with our rise. It starts off at 0. And then it goes all the way up to 10. Therefore our rise is 10. And our time frame is 0 to 5. Therefore 5. So rise over run, or change in distance divided by change in time, 10 divided by 5. So at 3 seconds, so at 3 seconds we have 10 divided by 5, which gives us 2. Don't forget, units, meters and seconds, therefore our units are meters per second. Okay, that was easy enough. So what about part B? So 15 seconds. So at 15 seconds, what have we got? So let's find 15 seconds. It's over here. And once again, it is a line which is sloping. So how are we going to work out the speed at this point? Well, just like we did with the first one, we need to calculate the gradient of the line. And just like I did with the other one, I'm going to make my triangle as big as possible, right the way across there. Okay, so what is our rise and what is our run? So the line goes up 10. So it's going from, in fact it's not really rise, it's fall. So it goes from 10 all the way down to here, which is 0. So it has dropped by 10. And the time period for that is, well, it started at 8 seconds. Don't forget, it didn't start at 0. It started at 8, and then it hit the bottom at 18 seconds. Therefore, the time period here is 10 seconds. So our speed would be our change in distance, which is 10. It's dropped 10 over a time period of 10. And 10 divided by 10 is 1. Don't forget our units, meters per second. And do our answers make sense? Yes, they do. Because if we have a look at from A to B, you can see that this line over here, this line is much steeper than this line, the line that we've got there. Therefore indicating that from A to B, it is moving at a greater speed than it is from this other part, which I suppose I could call C to D. If I just call that B, C and D. So from A to B, call this A down here, the object is moving at a much greater speed than from C to D. Okie dokie then, so that's our first one. So let's have a look at our next one then. So we have the graph below shows a toy car moving around a room. So once again, I'm going to have a look at my axes, and I can see that it is distance again. So this is again a distance time graph, and this one I'm going to do a little bit faster. So describe the motion of the car over the 26-second period. So let's have a look. 26 on the bottom is here. So yep, once again, they want us to describe the entire journey. So what do we have? Okay, so let's put some crosses on this. So we start there, move up to there, stay there, and then drop down to the bottom. Okay, so from 0 seconds to 12 seconds, so from 0 to 12 seconds we have the object is, well, its distance is increasing, and it's increasing in a uniform pattern, therefore we know it is travelling at a constant speed. Okay then, so our next bit, from 12 seconds to 14 seconds. So from 12 to 14 seconds, the object hasn't changed its distance, therefore the object is now stationary, it is now not moving. Okay, and then our last bit from 14 to 26. Now this one's a little bit tricky because it's a curve. So because it's a curve, we know that it's not uniform. We know that it is changing its speed, and because the gradient represents speed, it's changing gradient, therefore it is changing speed. But how is its speed changing? Let's have a look. So if I just draw some lines on this, some straight lines, some tangents as best as I can, you can see, I'm hoping, that the gradient of that curve is decreasing. In other words, the graph is becoming more shallow. Don't forget, the gradient represents speed, therefore this object is decelerating. Okay, but more than the fact that it's just decelerating, it is moving in an opposite direction. It is no longer moving forwards, it is moving backwards. So I would say that this object is moving backwards at a decreasing speed, or it is decelerating in the opposite direction. Okay then. Number 2, calculate the distance travelled by the car. Relatively straightforward. Let's just get rid of this. Okay, so calculate the distance travelled by the car. It doesn't give any time, so I assume it's for the whole journey. So let's have a look. Starts off at 0. Its highest point is up here, which is 80 meters, and then it goes back down to this point, which if I trace across is 8 seconds. Okay, so the object moves 80 meters forwards, 18 meters forwards, and then it comes backwards from 18 to 8, so therefore it is going backwards 10. So it moves 18 forwards and then it moves 10 meters backwards, therefore the total distance there is 28 meters. So that is the distance that the toy car has moved. And then number 3, calculate the speed of the car in the first 12 seconds. It's important that you read the questions carefully. It does say at the first 12 seconds. So it only wants you to work it out up to this point, which is handy because it is actually a straight line. It would be a lot more difficult if it was a curve. And in fact, for GCSE physics, they won't get you to calculate the gradient of a curve. So just like with the last one, we need to work out the gradient for speed. So it is rise over run. So what is our rise? It starts from 0 and travels all the way up to 18 meters. And the time frame is, well, it starts at 0 and 12. Therefore, we have 12 seconds. So to calculate our speed equals distance divided by time taken, or rise over run. So our distance is 18 meters over a time period of 12 seconds. So 18 divided by 12 gives us 1.5. 1.5, don't forget our units. Speed is meters per second. So that would be the speed of the object from 0 to 12 seconds, 1.5 meters per second. Okay, right then, our next one. So the graph below shows the motorbike, or shows a motorbike, pulling away from some traffic lights. So let's look carefully. This time it is a velocity time graph. So therefore we need to keep this in mind when we are answering the questions. So question number 1. Describe the motion of the motorbike during the first 8 seconds of the journey. So there's 8 seconds. So once again it wants us to describe the whole journey. And what does it show? Well, start off with the velocity is 0, and then as time goes by the velocity is increasing. And it is a straight line, so it's uniform. Therefore we know the object is accelerating at a constant rate. Okay, and then up here we have, well, its velocity is not changing. It's at 14 meters per second. That's not changing for the last few seconds. Therefore, it is travelling at a constant speed, or in this case, let's change that, constant velocity. Let's not confuse people. Constant velocity. So, how would we write that in an answer for a question? We'd say from 0 to 4 seconds, the object is accelerating at a constant rate, and then from 4 seconds to 8 seconds, the object is travelling at a constant velocity. That was easy enough. Okay then, question number 2. Calculate the acceleration of the bike. So, calculate the acceleration of the bike. Now, if you remember back, it is the gradient of a velocity time graph, change in velocity over time, which will give us our acceleration. So, how do we calculate our acceleration? Let's rub all of this out. Okie dokie. So, acceleration of the bike. So we start at 0 and we go up to here. That's the only point where it's accelerating, so it must be this part of the graph they want us to calculate. So we need to once again calculate the gradient of the line. So how do we calculate the gradient? Rise over run, or change in velocity over time. So we start off at 0 and it goes all the way up to 14. So our change in velocity is 14 meters per second, and our time frame is 0 to 4. Therefore it is 4 seconds. So we have 14. So our acceleration equals our change in velocity, which is 14, over our time taken, 4 seconds, which gives us 3.5. Don't forget, you need to make sure you have your units. It is acceleration, therefore it is meters per second squared. Okay, let's look at question 3. So calculate the distance travelled in the first 8 seconds. Okie doke. Let's have a look at this. So, 8 seconds, starting from 0 all the way to 8, calculate the distance travelled. So if I separate this shape up, I have a triangle there, and I then have a quadrilateral there. So, let's calculate it. 0 to 4, and from 0 up to 14, and then here we have from 4 all the way to 8, so that's a distance of 4 as well. So it's given us a rectangle and a right angle triangle. So let's calculate this. Half base multiplied by height. Well, half the base, half of 4 is 2. 2 multiplied by 14 is 28. Don't forget its distance, so it's in meters. And then for the next 4 seconds, we have 14 multiplied by 4, which is 56 meters. Okay, so then to calculate the distance of the motorbike for the entire journey, we need to add the 28 and the 56. So total distance is 28 meters plus 56 meters, which is 84 meters. So that is the total distance travelled by the motorcycle. Okay then, let's look at another one. So the graph below shows the motion of a car during its journey. So our first question, describe the motion of the object during the first 30 seconds of the journey. So it's from 0 to 30. And right, it is a velocity time graph, therefore I need to keep that in mind. So let's go through this nice and quickly. So from here to here, its velocity is not changing, so it must be a constant speed. or constant velocity. Then the next part, it drops, but it is a straight line, so we know that it is uniform deceleration. So it's decelerating. Then down here we can see that the object is still moving. It's not quite hit zero. Zero's here. It's not hit zero, so it's still moving, and it's moving at a very slow constant velocity. Then from 15 seconds up to, looks like 18 seconds. And these lines aren't showing up very well on my board. I think it's 18 seconds. You can see that the velocity is increasing. It is a straight line, therefore it is accelerating. It's accelerating at a uniform acceleration, or accelerating at a constant rate. And then finally from 18 seconds to 30 seconds we can see the velocity is not changing. So once again, it is a constant velocity. So there's quite a lot to that one. So we have constant velocity to start with. We then have deceleration, uniform deceleration. We then have a constant velocity. We then have acceleration, uniform acceleration. And then finally, constant velocity to finish. So next one, calculate the deceleration of the object. So we need to be looking on the graph where we have deceleration, and deceleration must be where the velocity is dropping, because deceleration means slowing down. Therefore they must be talking between there and there. So what do? Calculate deceleration, or negative acceleration. It is the gradient of the line. So I need to do rise over runoff, the drop in velocity divided by the time taken. So if I have a look at the first point starts at 3. So that's at 3. And then this point is at 9. So the time taken there is 6 seconds. And it has dropped from 21 meters per second up here all the way down. Whoops. All the way down to here, and that point is at 1. At that point there, so it's dropped from 21 to 1, therefore its drop is 20. So it's dropped 20 in 6 seconds, therefore our acceleration, or should I say deceleration, but it's just negative acceleration, is our change in velocity divided by our time taken. Now this isn't going to give us a very good answer. It gives us 3.3 reoccurring, so I'm just going to call that 3.33 acceleration, so it's meters per second squared. Okay, so that's the acceleration. Now technically it's negative because the object is slowing down. It's dropped down by minus 20, so technically speaking it's minus 3.33 meters per second squared. Okay, and our last one, calculate the acceleration of the object. In fact, I think there might be another question after this. So, calculate the acceleration of the object. So we have acceleration is between there and there. Once again, we just need to work out the gradient. So we make our triangle, and then we do our rise over run. So that's gone up to 16. And it started at 1 down here, so 1 to 16, it's gone up 15, and our time taken is, well, it started at 15, and this point here is 18, so that's 3. So this one's a little bit easy to calculate. So our acceleration of the next part is rise 15 over the run of 3. 15 over 3 is 5 meters per second squared. And that makes sense. It is greater than the deceleration, and we can see that just by looking at the graph, because of the fact that if I just rub these lines out, you can see that this line here is much steeper than that line is. Okay, and then our last one. So calculate the distance travelled whilst the car was accelerating. Now this is a question that's very easily misunderstood. and you can quite easily lose lots of marks on this just because you don't read the question carefully. So very carefully read it. It does say whilst the car was accelerating. So they don't want you to work out the entire distance travelled, simply from this point to this point. Now the next thing that sometimes trips people up is the fact that if you draw this carefully, you can see that actually it is not one shape, it is actually two, because the fact that the line doesn't start at 0. There is actually a small box down here which people quite often forget to calculate. So let's work these out then. To start off with, we have our values. So the top value up here is 16 and our bottom value was 1. Therefore we have a rise of 15 meters for this triangle, and the base we know is 3 because we've calculated, well, we looked at that for the last question, so that's 3. So therefore we have 5 multiplied by 3 and then halved, or half of 3 multiplied by 15. And also don't forget we need to calculate the area of the little box, which we have 3 and 1. So we'll start off with the area of the little box, which is the easy part. So the distance equals, for the box, 3 multiplied by 1, which obviously gives us 3 meters, and then we have our triangle, which is 15 multiplied by 1.5, which gives us 22.5 meters. So that's the area of the triangle, and that is the, oh sorry, wrong way around. That's the area of the little rectangle, and that is the area of the triangle over the top. So the total distance travelled is 25.5 meters. We just add those two together. Okay, so that's the total distance travelled whilst the car was accelerating. It's important to read the question because you could quite easily spend some time trying to calculate the area of everything, the area underneath the graph, and you don't. You only need to work out the area underneath the graph where the object was accelerating. Okay, then just a little quick mention of some acceleration which is not uniform, and this is something that they do sometimes ask in exams, and I am just going to glance over this very, very quickly because I know that I'm very closely approaching the 30-minute mark, making this video a little bit longer than I'd like. So anyway, let's talk about this very quickly. Describe the motion of the object shown by the two graphs. So starting off with, they are both velocity time graphs, and let's see what this one shows. So start off with, our gradient is shallow and it is getting steeper. Then we have, it is steady, it is neither accelerating nor decelerating, so it is a constant speed. And then we have a gradient which we can see is also increasing there. So what does this show? Well, if in our first part we can see that the gradient's getting steeper, it is still moving upwards, still a positive correlation, so to speak. So it is accelerating, but the gradient's getting steeper as we go. So it's accelerating at an increasing rate. Then up here we have our constant velocity, and then we have it's decelerating, it's dropping, so we know at this point it is decelerating. And we can see, once again, the gradient is also getting steeper. It's almost dropping off a cliff. So we know it is decelerating at an increasing rate. So it's slowing down the whole time, but it's slowing down by greater amounts each time. Okay, let's look at our second graph then. So our second one shows that we have, if we just draw some tangents on here, we can see that that is showing that the gradient is getting shallower, yet it is still increasing velocity. It's still moving in an upwards fashion. So for this one, we know that to start off with, we have the object is accelerating, but it is accelerating at a decreasing rate. and then we have constant velocity again, and then this one we can see starts off very steep, and then as time goes by the gradient is getting shallower. So this one is decelerating because the velocity is dropping, so it's decelerating, but this one is decelerating at a decreasing rate because the gradient is getting shallower at a decreasing rate. Okay, and that is it for velocity time graphs, distance time graphs, and motion as a whole. Thank you for listening.